this. I don't know why. Maybe I'll stop putting out the recordings. That'll really screw up Brandon. That'll really screw up Brandon. So get your peers to come to class, Brandon. What's that? No, I think I don't want to say that, and then someone not being here. 3, 6, 9. We're all here. Wow, thank you for coming. Well, I mean, you all haven't been here for like at least a week now. You have, but I said we haven't had a full class. Okay? Not that people have excuses. You were the only one missing, Amanda. Okay? And no one else had an excused absence like you either. Okay? They just decided that they had picked their priorities, right? They're just too busy. Too busy for me.
I did. I think maybe you don't remember.
What's that?
I missed the class that I taught you.
Oh yeah, that was but that was when Adam came.
Oh yeah.
Yeah. No, I'm talking the the last week or so.
Oh,
No, you're solid, Daniel. I got you. All right. Oh shit, what happened here? This is not good. Oh, that's why. What are we going to talk about today? Well, we're going to try and get through more than we have been getting through, but as long as you guys are getting value out of this, I have no problem deviating, okay? All right? As long as it's a benefit to you guys. It is kind of tough, as you probably noticed, Amanda, there's a lot of board work, right? And so if you have any questions, just try and visualize what I'm talking about. Yeah. So if you do have any questions, come talk to me, okay? If you do miss a class and then you're listening and
You
don't know
can
what's
draw
going
on
on.
that.
Yeah, but then I have got I guess I could. I just like this better. I don't know if you notice how many times I walk over there, and there's no reason why I should walk over there. I just like to walk over there, okay? I will take that into consideration, thank you. So, we did get through modeling and discretization, right? These huge jumps that we're making from the real world to the mathematical model, and then finally we're taking that mathematical model and we're discretizing it, we're putting it into a finite element model. We try and match everything that we possibly can, as close as we possibly can, in an effort to just highlight the thing of interest that we're trying to get out of our model, right? Whether it's the base reactions, whether it's the reactions in a beam to design a beam in a brace frame, connection demands in a moment frame, right? If we're designing the foundations, we might do something different. And everything is tailored to what do we want to get out of our model, right? So we make a lot of simplifications, which we did that. When we're doing that, right, documentation is incredibly important. And I asked for some of that in the homework. I haven't looked at those. I'm a little scared at how brief those are probably going to be, right? You cannot have too much detail in those, right? Why would we want to document it? There's 5 reasons why you would want to document it. Give me yes, Brandon.
Not get sued.
Not get sued. Litigation. Solid. This is huge. Huge. We had a project in the Yellowstone Club we were doing, and we had it was essentially a bunker underground, okay? And the contractor made a messed up, and they used the wrong strength concrete. It wasn't strong enough, okay? It ended up going to lawyers, right? Because the contractor was dead set on the fact that we were over conservative with our calculations. We had to then package our calculations up, send them to 2 other reviewing structural engineers that they had to do third-party reviews to verify whether or not they felt like what we did was reasonable, and that if there were any other ways in which we could get around the fact that we needed 4,000 psi and they had 3,000 psi sitting there in place.
There's 3,000 people.
You know, they screwed up when they sent the mud, and so when they were testing it, right, they came out short. They ended up coming through and having to water blast out this entire underground bunker basically. Okay, super expensive. So we wanted documentation. In that documentation was a lot of what we'll show here in a little bit. Written language, talking about what we were doing, but also little diagrams of the model, right? There was a VA model of concrete and concrete posts and beams and figuring out stuff, telling them what we used where, what the material properties were, right? All of that. And so litigation is huge. Is there another part part of what we do that would help to have documentation? Yes, Brandon.
Honestly, just communication between coworkers.
Dude, fuck yeah. During design. You know, Brandon's really crushing it today, guys. I might just give him a password.
Whisper.
All right, step it up. Step it up. What's another one? Yeah, during design, right? You might not be working on the same project throughout its entire duration, and you might take your calc binder and pass it over to somebody else, right? I did that when I quit, right? I had multiple projects I was working on. I had calculations I was working on. I just said, okay, here you go, right? Right, here you go. And they needed to be able to go back and figure out what the hell I was doing. Another one.
I mean, this is kind of related, but coming back to a design after a long time.
Yep. Man, you guys are really crushing it. Retrofits. Renovations. Right? There's been multiple projects where we actually, more summarily, when I worked there, we would get a phone call because the owner, when they looked at their documentation for their building, the structural drawings had our name on it, right? So then they came to us, and we had the ability, most of the time, there were some projects we didn't, but most of the time, we could go back into the archives, which was basically a big storage room with a bunch of files, and go and pull out that calc binder for that project. And so we started ahead, right? And that's the reason why they called us, is they said, okay, you designed this in the first place. Can we put a piano in this living room? Can we do this? Can we do that, right? Can we knock this entire wall out? So definitely, it's good to have documentation for retrofits and renovations. Right? As I mentioned with, well, give me another one.
Permitting.
What's that?
Permitting.
Yeah, I guess I was gonna say construction admin. Administration, right? They call it CA, okay? It's the lingo. Construction admin. When you're out there and you're running a project and you're trying to get things done, the contractor, one, omits something and forgets to do something, okay? Maybe they put 3 anchor bolts in and they needed 4, right? Maybe they don't have enough projection to get a plate washer on there that you asked them to put on there, like in a brace frame or something, right? And so you need to be able to go back to the calcs and figure out, how did I do this? What was I doing? Can I omit this? Can we not omit this? How can we change things? So in the construction admin side of things,
Future projects.
I was gonna say third-party review. I said retrofits, renovations, we can call this future projects. Right? Any of the buildings on MSU's campus goes to a firm called Eskil. They are in California, right? 'Cause we have to get a permit from the city of Bozeman, and when you do any project in the city, right? And so you submit construction documents. Well, they also require you to submit calc packages. Okay? So we would scan hundreds of pages of calcs, and they get sent off. The city of Bozeman, they know, to their credit, they know that they are definitely not qualified to be reviewing structural calculations of that magnitude. And so they send it to a firm in California that's all they do, okay? So then they come back and they'll say, you forgot 6.6.3.2.1 in ASCE 7, right? How did you account for this, right? We didn't see it in your calculations. Like, that's how detailed they get sometimes. And so making sure that you document, when you're even going through and figuring out your loading, going through and just adding in code references, right? Where did you get that? What are you trying to deal with, right? In the seismic manual, right? Or the ACI or any of those, right? We want to reference back to those codes because there's a lot of times that we get third-party reviews, right? Yes.
Can I ask a question about the construction admin?
Yes, for sure.
How did you approach like telling contractors like you're wrong, like keeping a good relationship with them, but also like
It's a
saying-
game.
Yeah.
It's definitely a game. I would say that the best projects are the ones where everyone is more focused on having a quality product in the end and having like a good project, to where they're looking at the end game and they're not looking at you arguing with them about one little thing out there at that certain day, right? And so it depended on the contractor you're working with, or even the owner or the design team, like the architects or other mechanical, electrical engineers, right? If everyone's looking out and saying, okay, today, yeah, it might be a shitty day, we ran into something that isn't great to deal with, but there's always a path forward, we can always make things work. Knowing that, I mean, I would keep track of, I'd have like at Morris and Merlin, we had like a construction log, where if you did something for a contractor, right, that felt, I mean, it was kind of doing them a favor, you could write it down in there, and so that you could keep track of this, like, all right, how's the scale tipping, right? So that when the contractor comes to you and says, wow, you're really like killing me today, like I can't do this, you know, it's like, hey, John, I helped you 3 weeks ago and did this, right, after hours, or like, we were able to let you go on this, like, help me out here. It's really a game. I don't know that there's like a recipe for dealing with that really well, other than just, you know, maybe focusing on the bigger picture and trying not to let them focus on like today's incident. But they could also like, just knowing that everyone has bad days too, right? And so they could be blowing up over something that really is not that big of a deal. Like I've said it before, I think, don't be afraid to tell them that you don't have to give them an answer right away either, right? I mean, be punctual, right? Be on time, right? Don't let them feel like they're waiting on you, but you don't have to give them an answer that minute while on site when they bring you over to this column. Like the Rendezvous Dining Pavilion, I remember the big tall column, it spans like 30-something feet right out in the front in the, what would be the northeast corner. Someone with a forklift backed into it and broke it off the pier, right? And so like we were like, oh fuck, you know, and the contractor's like worried about it, and so you know, you just like, I didn't give them like, oh, you need to do this, this, and this right now, even though it was, I mean, it's like, damn, that could be bad, right? So we like tone it off, and you don't have to give them an answer right away, right? So. But there were times I worked in a project in Alaska, we were working on a conveyor, and if the conveyor wasn't running, we like shut it down for a week of 24 hours a day construction, and if they weren't able to turn it back on at the end of the week, then they were going to be losing, I think it was like $1 million an hour or something stupid like that. And so like there was a lot of pressure, and I had to like, we had to like go back into the Ford F-150, and I was running calculations in the front seat of the truck, right? So that I could just walk, like, again, I didn't tell them like do this, this, and this right now. I said, hold on, let me think about this, wrap my head around it, get back in the truck, feel good about it, maybe make a phone call, go back out, give them an answer. Right? There's always other things they can do. So it's not, it's just like, yeah, it's a game. It's a game. And some people do better with, you know, some people than others. We had engineers at Morrison Merrily that wouldn't work with certain contractors or certain superintendents because they just did not get along. They had projects that didn't work. And so you just ended up, yeah, you might design the project, but when you went into CA, you had a different engineer manage it because the personality-wise, they just didn't get along. And that happens, right? We don't have to be friends, right? That's another thing. It's like, I'm not out here to make friends. I've got plenty of those back home, sort of thing, right? And the other line I used a lot was like, we're not building a fucking treehouse, right? This is a real building, right? This isn't like, we're not doing something in your backyard. So, all right. Does that help, Ethan?
Yeah.
Cool. So, documentation. What does it usually include? Well, description of our mathematical model. What are some of the elements that we would describe that come from our mathematical model?
Loads.
Yeah, loads. Are there special sources for these loads? Directions in some cases? Right? What are some of the other elements that we have in our models that we'd want to describe? Boundary conditions or supports. Springs. What type of, wow. Fixity. All right, releases. What other elements are out there?
Assumptions,
I guess I'm looking for real like elements.
members.
Members. You want to describe members. Materials. Especially with concrete, right? Releases. Etc. We've got areas we use sometimes. Spans, maybe loading type. Does it only load members? Does it load members and braces? A lot of times we have plates. Again, materials, releases. Right, all important things. So we have description of mathematical model elements, right? What are we actually putting in our VA model? Right? And what are some of the details associated with those elements? But we also have a description of the intent of the model, right? What are we trying to do? Are we doing a lateral analysis? Gravity analysis. Are we doing a specific element design? Right? Maybe you're doing a model and all you're modeling is the wall, the foundation walls on a residential building, right? So you don't even show the footings in there, right? You just pin the base. You're assuming it's getting pinned by the fact that there's a slab in the basement, right? Maybe you don't even model the floor framing system. You assume that it's getting pinned at the top of the wall system. So you have just a series of walls, which is just your foundation of your, residential building or even a commercial building. Right? So you just do a specific element design. So you want to make sure that you mention that, okay? You want to make sure that you describe some of this. I would say describe some of this or reference the naming convention for your models in the in your folders, right? In your archives for your business, right? At DCI, you might have a naming convention for VA models, right? At Morrison Maryland, we tried to be pretty concise about what we were doing. If it was a gravity model, we mentioned that it's a gravity model in the description, right? In the name of the file. Make sure there was no confusion. We might even reference that file in the calcs, making sure that someone going back for a retrofit 5 years later, they go back to that folder out on the drive, they can actually find that exact file, right?
I think people sometimes say that their initials on it.
Yeah, definitely.
No.
Yeah, that would be a very good idea. You're doing all that, aren't you?
Everything's in the cloud at Hicks. We're
Oh, that's totally fine. That's in the cloud. That's fine. But you have a place for it, right? You have.
yeah. Well, there's a
Folder
subfolder for
paths.
every project.
Yep.
It's
So you
got
have a repository. Yep. But then in there, right? If you were looking at a
Gravity,
project
lateral.
file, right? A lot of times too, when you're working in construction and CA, a lot of times people will go out there and they might manipulate one of those VA files to see if something works, right? And then they go and they save it to that folder. And then 3 years later, you go back out there, and if the naming convention, it's like,
Construction updates.
you could, right? So it's like shit like that. So just making sure that there's something out there that delineates files for their purpose, whether it was during construction, whether it was during design, if it was just for the lateral analysis, just for the gravity analysis. Very helpful here, 3D views, right? Or renderings. I haven't looked at your homework, but printing off the VA model in the picture view or something, or even just the normal VA model and just putting arrows to it, right? So like these were this is norm, right? So if we go back down here to our model, right? Being as simple as saying pin base column. Right? Fixed RZ. Yes.
This is gonna be off topic, but why did they choose to model it with those rigid links? Like to group the modal mass on the plates versus.
Oh, you're reading the actual thing.
Yeah, I was reading.
Wow.
Yeah.
Trying to catch up or what?
Well, I don't know. I was
Right
just
here?
curious.
Why do we do that? We did that because we
So
were
you don't get- Go ahead.
we were trying to spread out that mass into the diaphragm the best we could
Messing up your plate or something?
without
What's the
so
point of the rigid links?
so yeah, so the reason why the rigid links are there is that it's an infinitely stiff member. So in VA, if you go and you model a member, if you go over to the, the type of member, you have standard parametric, you have your database shapes. Well, also in there is an option to do a rigid link. What a rigid link is an infinitely stiff member. So when it's fixed, like it does not move, right? It's not going to deflect. It's going to be a straight line regardless of what its orientation is. So what did it do here? Well, it allowed us, and we did this on, this is NAIC, but it's also like Miller dining halls, okay? We put the mass of the diaphragm at a given point. Well, if we loaded that one node, because the reason why we're doing this is some of you guys haven't had dynamics, okay? But seismic demand is all based on mass, right? So like wind loads based on projected area. Seismic load, it's all based on mass. So like we are physically accelerating based on the excitation of the ground, right? So the load doesn't come from outside, it comes from within each of the members in the building. Well, when you do, there's 3 different levels of seismic analysis. We have equivalent lateral force. That's saying that we're going to punt as engineers and be very simplified and say, okay, right, it's all based on mass. It's actually pretty complicated. But we're gonna say, fuck it, we're gonna just distribute the load, right, at each of our diaphragms vertically in an effort to mimic what the building would look like if it just rolled over with what we would call our first mode of vibration, right? The second one, which you end up having to do if your building is in certain categories, has certain what we call irregularities, right? Then you jump into what we would call a modal analysis. What a modal analysis does is instead of actually physically shaking the building now, right, we're getting to that point. Before we get to that point, they say that, okay, you can simplify the analysis. It's going to be more in-depth than our punting method, where we're actually going to start considering the stiffness of our model and the mass distribution in our model. And what we do is we end up looking at, well, what's the natural frequencies of our model? Well, if you guys are in dynamics, the natural frequency is square root of k over n, right? It's a function of the stiffness and the mass. So everything that has mass and stiffness in a model will contribute to the natural frequency of that model. So what happens if you leave self-weight on in the model? Any ideas? So if you leave self-weight on, so every member in this model has self-weight, has mass. If you leave that on, what do you think will happen?
You get a mode for every.
You get a mode for every single member, which destroys the ability to actually analyze it, right? And so as an engineer, you have to think about, okay, what am I really trying to capture out of this? Do I care that at, say, 150.2 hertz, that this beam over here is gonna start vibrating up and down, right? That's really not gonna give me anything relative to what my moment frames in this building really care about, right? And so what we decided to do was hours and hours of discussion of how to simplify the model effectively in order to capture the behavior of intent, right? The behavior of what's going on or what we really want to see out of this without oversimplifying. So what we decided to do was, okay, we've got this mass. Most of the mass, we could say, lumps in the diaphragm. We're gonna take half of the mass above and below, right? We're gonna put it into this diaphragm. Now we're gonna start pushing on this diaphragm. Well, we don't want, if we distributed that mass into all like 100 nodes around this diaphragm, we still are gonna get really weird natural frequencies that might be in the vertical direction that aren't gonna contribute to the lateral demands on these frames. And so what we ended up doing was we would create mass on a node, and then we're going to reach out, we're gonna connect it to our diaphragm. And we had to connect it to our diaphragm in such a way that we're not adding to the stiffness of the diaphragm, okay? But we're gonna be pulling on it. And so that's what this is all about, is saying, okay, we've got a node with mass, okay? And it's sitting out here, right? We're gonna put it out in the center of mass of the diaphragm. The other thing in modal analysis you have to take into account, right, in seismic design, we're guessing at where the mass is, right? As engineers, we're making a lot of guesses. Okay? That's why in load combinations for ASD and LRFD, that's why we have 0.6 dead and 0.9 dead, because we are guessing when we're designing Roberts Hall as to what it's actually gonna weigh now and also in the future. It might change use, right? And so we do the same thing in seismic demand, is that the code recognizes the fact that we're guessing that we know where all the partition walls are, right? All the exterior wall elements, what everything is made out of. And so we're gonna not be super accurate of where that center mass is, right? Because the center mass is really gonna be where the force is, because it's all based on acceleration, right? And so in this case, we guess where that modal mass location is. We're gonna do an accidental eccentricity value that the code requires us to do, right? 5% of the lateral dimensions of our building. So we end up starting to move this node everywhere. Well, it gets pretty complicated if you had 100 of these mass nodes spread throughout their diaphragm, and we have to start moving all of these in all of these different models. So we decided to say, okay, I'm gonna lump the mass in one point. On top of that, I don't really care about the diaphragm going up and down, right? In the modal analysis method, they require you to have, is it 85% modal mass contribution? Or 80%? Anyway, you guys just took the class, right?
No, it's not till this fall.
Come on, it should be there at least.
It's not till the fall.
Right, so you have to get a certain contribution of the model's total mass, right? And that allows you to say, hit the stop button and say, okay, I've seen enough of the mass of the building, I've seen enough of the natural frequencies, and each mode has a contribution. And so we found through going through a bunch of analysis that you could actually support this node, support it against vertical translation and rotation. I don't really care about the fact that this node bumps up and down, right? So it's really, I'm just looking at how does this building push or slide side to side.
Is that one node per level?
One node per level. And then we kind of have this kind of cross that runs out into the diaphragm with rigid links, and each of these rigid links is released on the ends in the weak and strong axis bending. So it can rotate, because we're really trying to just drag that mass around in the diaphragm, right? And so we don't want the fact that we have this infinitely stiff cross sitting in this diaphragm to affect the in-plane bending of the diaphragm, right? Because that plays a huge role in how that mass and effectively the loads are distributed in the building.
What are those nodes fixed, like, norm is super irregular, and it's more of a rectangle rather than a box. So what are those four nodes connected to?
These four nodes out here,
Yeah.
each one of these nodes, all 5 of these nodes, sit in the diaphragm and are connected to the plate elements of the diaphragm
Arbitrary locations?
at the center mass location.
For sub-diaphragms, or what?
In Norm, I didn't do that, Chris did. I'm assuming he would have to, because you're talking about the big clear story. The center mass
No, I'm
might
just
end up
thinking,
being
like, where do you choose to put the
Other
locate
four.
his cross, you know, like, you know where to.
engineering judgment, man. You
Yeah.
just like look at it, you're like, all right, how far should I extend this out? You know, trying to get out into like the field of the diaphragm where we're trying to grab things. You might not want to put a node where you're dragging that right on top of a frame, right? That's sitting right below it. Because now you're gonna be dragging right on that frame, but you are not physically doing that in the real world, right? The diaphragm's got to do that. So you might not want to put it like right on top of a beam that's in line with the moment frame below. Does that make sense? You start kind of walking through the load path and how, you know, your decision on where those nodes are affects the outcome.
So did you get load transfer through the rigid link to the diaphragm at all, or is it only through your?
Yeah, so that's what the rigid links are for, is to say, okay, obviously, if I put the entire mass of a building at one floor level in one node in the center of this diaphragm, and that's where all the load's coming from, you're gonna just destroy your diaphragm, right? That was one of the big things. And so we decided that we needed to, okay, spread that out. Well, what is the most efficient way to spread that out? Well, that's why we decided to go with the rigid links. All that's saying is that when this node moves, these rigid links don't compress or expand axially, right? And so they're connected. And the stiffness of how they're connected is based on the diaphragm stiffness and not those member stiffnesses. That's why we released the rotations of them.
How does it act integrally with the diaphragm if you're only
Because
connected
those
at two
nodes, those nodes share nodes with the plates in the diaphragm.
But like the rigid link is not deflecting in, I guess it can rotate.
Yes, it can rotate with the diaphragm. So if the diaphragm, like,
I'm thinking of like, does a rigid link have like a shape function that's like that would match? I guess
It's-
the rigid link is.
the rigid
is
link-
just straight the whole time.
yeah, so the rigid link does have a shape function. I mean, it has to. But its shape function is such that it does not displace between nodes. Right, it's gonna be a linear display, like, it's gonna be like a line element without transverse displacement. It's truly like infinitely stiff. It cannot bend, it cannot expand, like extend or contract.
Did you guys go through different iterations of where to place those nodes?
Yeah, it took hours and hours. This concept started when we did the Miller Dining Hall between hedges. Because we had to do a modal analysis on that building, and that was honestly the first one we ever did, and I mean, that was like it's a circular building. It's like got concrete shear walls in the basement level for half of it, because it's a clear basement at the bottom. So it was just like super irregular, and so we had to do modal analysis, and then we started like saying, okay, we started running it, and you'd hit run, you'd come back the next day, and it was still running. It was like, okay, we gotta make some simplifications. So then we start like paring things back and realizing, looking at all the natural frequencies and modes, we're like, oh shit, there's a beam that's on the penthouse that's doing this, and it's not contributing to our overall behavior that we're trying to capture, right?
So was the node that has the mass loaded with it not connected to the plates?
No, it is. It's all of that is at the diaphragm level,
Will,
right?
would the rigid links still be able to spread it all out? I just feel like if the plates are connected to the one with the mass, then that's just gonna sabotage everything.
Well, the fact that these are rigid links says that if this node moves in any direction, right?
Pulling on the other nodes.
Yes, it has to move everything else the same amount. That's why the rigid links are a benefit.
And then VA calculates that stiffness that goes into each diaphragm that contributes to each like
Yes.
mass, like.
So,
You don't have to worry about
It
that.
calculates it based on, yeah, the mass location and the stiffness.
And you give it like an excitation that it runs through.
You don't give it an excitation. What you end up doing in the modal analysis method is you are essentially summing up the contributions of each of your modal, like, natural frequencies. So like one of them, like if you had a 3-story building, one mode is going to be like the building just keeling over in one direction, right? And then another node is like the building's gonna do this, right? The second story is gonna move over, the top story is gonna move that, right? And each one of those is gonna have a certain amount of mass contribution. And then even the modal analysis method, you're punting, because in the end, all you do is square root of the sum of the squares of all the contributions. Which is fucked up, right? Like,
so I feel like in dynamics, we just did everything by its own self-weight and then added on dead loads from the building that was gonna be added to it. But that was also because it was a very regular, symmetric building. Would it be okay to do it that way if you did have a more regular symmetric building versus a big crazy building with a bunch going on?
I would just say that, I mean, if it was simple enough, VA might be able to chug through the whole eigenvalue, eigenvector problem of figuring out your natural frequencies and your modes without taking hours, if not days, to do it, right? Because everywhere that there's mass, we have stiffness, right, to hold that mass, and therein lies, we're gonna have to have a natural frequency associated with it. And so if the natural frequencies were such that we could calculate all of them, because the building's simple enough, then yeah, you might not have to do something like this. But this is the method that we landed on. I'm not sure how RAM does it, they do model analysis too. So, and you're probably a Jedi with model analysis and RISA, right, son? Yeah.
And have you ever like seen like, I don't know, have you ever seen an earthquake hit a building? Like, you just have to say that you made the measures, but I wonder if it actually like works, like when there is an earthquake, you know, like.
Never, not gonna know until we know.
It seems like so.
Fucked up, right?
Such a guess.
Yeah, it is such a guess.
It's like
We are
so much effort.
educated guessers, right?
And then the other
It
one-
has to be defendable, because even if it does fall down, you go back and say, hey, did you follow the intent of the code?
Right.
Right? And really what they hold us to is the standard level of care, is the definition of what we can get sued for, right? Are you really meeting what the expectation is in our industry and in our society of what we should be doing as engineers? And I'd say like people that are uneducated in what we have to do every day to like figure this out, right? The guesses, they expect us to know exactly what's going on. So you gotta like argue that with a jury of your peers, right? Which are not gonna be structural engineers, or at least the prosecution is gonna load that jury up with people that are not structural engineers. Because they're gonna say, what the fuck, it fell down? Like he's supposed to, like he or she's supposed to keep that thing from falling down, right? Yes, he goes to jail, right? So hopefully, I mean, I felt comfortable with this. We felt comfortable doing it this way. There's a million other ways you could try and do it, right? There's a million other ways. As long as you follow the intent of the code, that's the big thing.
Does time history only kick in E and F?
What's that?
Does time history analysis only kick in SDS or SDCE?
No, you could do time history in any seismic design category. I mean, you wouldn't do it for A, I don't think, because you're really only hitting the building with like 10%. But like in B all the way up, yeah, you could do it, but it would probably only really make sense in like D, E, and F, where you start seeing a lot of restrictions with respect to your ability to even use the equivalent lateral force procedure. Right, so you
Is
just,
that any
you get
faster?
time history.
In VA to just load it with an earthquake?
I mean, you can load it with an earthquake, but again, like, so that's the next step even further, right? So we have equivalent lateral force, we have modal analysis, then you have time history. Time history is you shake it with an earthquake. And the seismic code requires you to pick a suite of earthquakes, right? You have to pick like 3 or 5 based on where your project is located, what the soil type is, like all of these parameters. And you can go out there and they have generators that you say, here I am, these are my soil thing, and like boom, 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 here's the earthquakes you need to shake your building with. You load those earthquakes into VA, and then VA starts shaking. Well, what is all of that shaking, right? How are loads affected in your model? What's it based off of? Stiffness, and then the location of mass, right? So you better be very confident about where all that shit's at. And then these simplifications might be really oversimplifying. You wouldn't want to just put a mass at your diaphragm and then put these rigid links out there and then shake it with an earthquake. Because I feel like I wouldn't feel as confident with this method doing time history as I would with modal, because in modal, the effort, yeah, I mean, we're making some grand simplifications, we're square rooting the sum of the squares, we're really looking at overall behavior, whereas time history, it's like, we're shaking our building. And it'd be like putting Roberts Hall on a shake table and putting El Centro, which is a very, yeah, I mean, maybe, yeah, probably. But it's all based on stiffness. And then when you do time history, right, you probably would want to start thinking about, okay, non-linear behavior, because like, well, if you took Roberts, for instance, it's concrete, right? The second you push on it, it's gonna crack, if it's not already cracked now, right? So then that changes all the stiffness, right? You guys ever been in the basement?
Oh, yeah.
Yeah. Oh, you guys have it? Okay. Yeah. Put that on the list.
Did you know?
Exposed rebar, big like round cobbles for concrete, right? We were literally standing on a diaphragm. We're standing on a
Bunch of
slab,
places
elevated.
where the, like, punched through the diaphragm and there's just concrete poured out of
Yeah.
it.
Yeah.
Beautiful.
And the weird seismic graph.
Okay, we're talking like horses and plows and shit. Then like pictures of the construction of this building.
Did they ever like go back and take strings?
And do what?
Take the strings.
So there's it's called a Schmidt hammer. Has anybody heard about a Schmidt hammer?
Oh,
Yeah, we have one up in the lab. Sutton, what's wrong?
Isn't that where it's just like? you're
Yeah,
trying
it's
to find out
bullshit.
rock?
It is
Yeah.
fucking
It's
bullshit.
like, what?
Literally, yeah. You're like, it's literally like this little, I don't know, it's like an auto hammer where it's like, it comes out with this rod and then you just push it into the floor, and what it ends up doing is it takes a steel ball and it raises to a certain height, which is effectively a certain amount of energy. And when you get to the bottom, it lets the ball go and it bounces, and when it bounces, that height that it bounces, they've correlated that to concrete strength. So you just like, boom, look at the thing. Oh shit, yeah, we're at 3,500.
I tried that out against like cores. Actually.
Oh, you did?
Yeah.
Yeah.
For shits and giggles, because we had one in our office.
Pretty scary.
Yeah, I mean, I feel like it's like plus or minus 3,000.
Oh, okay. Just within the level of error that we like to test.
My FE had a question on a Schmidt.
What's that?
The FE had a question on a Schmidt hammer.
Oh, really?
On mine, yeah.
Yeah. I mean, we've
Compression testing is like plus or minus.
we bought one at Morrison Merrily to kind
Oh,
of do
that's pretty
that,
solid.
but then we ended up just coring it because we didn't feel super good about it. Okay. So.
You're down to 7 minutes.
Damn. So we've got, these are just some very short excerpts from some projects at Morrison Merrily and some descriptions of just some lateral analysis, right? And how we decided to model it and put nodes and how we felt about it, why we thought, right? With masses supported at these nodes, the nodes will be tied into their respective diaphragms using rigid links modeled as shown. Right, the configuration shown above allows for lateral translation of mass while providing minimal restraint to the diaphragm as it translates vertically and bends. Right, so we're just trying to explain to someone reviewing this what the intent of our model was and why we did it that way. Right, so we could defend it later on. All right, in this case, all we did was we took loads from a spreadsheet which we had, which allows us to take a rigid diaphragm. I don't know if you guys did that in concrete too. Okay, if you have a rigid diaphragm, well, you have a torsional contribution and a translational contribution of your shear in each of your lateral elements based on the stiffness of that. You can essentially, we just built a big spreadsheet that would distribute the load based on the equivalent lateral force procedure. Okay, then the code makes us do other things, right? Making sure we consider 100%, 30% in our two directions. That also is based on our, not our discontinuities, but our, what are the two tables? We have vertical irregularities, right? Lost it there for a second. So based on our irregularities, we have to do, now the code makes us like hit our building with all the seismic load in one direction and 30% in the other direction. It's like with wind loads, they make us do a quartering load, which will give us 75%. In our two orthogonal directions. On top of that, seismic loads, right? If our system isn't redundant, we got a 1.3 factor, all sorts of stuff. We talk about that. If we're doing stability in this analysis also, so we reduce the stiffness based on section C, right? Appendix C.
So on the bottom, it says 270 of 514. Was that all just the notes, or was
That was probably the
whole package?
what building was this? It may have been the full package.
No way.
It may have been. This building we didn't do in VA. Well, not the entire building in VA. We just took moment frames. This thing didn't even get built. It's supposed to be behind Kohl's. It's like an 8-story building with a rooftop pool and shit. It's supposed to be like a luxury condominium thing, parking garage in the basement sort of thing.
Oh, there's podium ones going up there.
Yeah. Okay. So, lesson there. Make sure you document. Document well. There's no such thing as not documenting, or like documenting too much, right? Making sure someone can follow. Okay. That's a hint on the homework moving forward, right?
But
Homework moving forward. Making sure you document the models that you create. Okay. Boundary conditions. Right, this is a huge part of the overall modeling process, right? We use this to constrain or release the model. We do this because we need to provide global stability. we're taking the inverse of K, right? Or VA is taking the inverse of K. We cannot have that thing being singular. Boundary conditions also, right? We constrain and release the model so that we can ensure the behavior matches as close as possible to the mathematical model. All right, we do this at connections and supports. And that's where we impose boundary conditions. We do it at nodes, right? So this interconnecting of plates, interconnecting of members, right? Where our model is ultimately supported outside, right? Our free nodes, where we have maybe just one element connecting to it. Boundary conditions, I'd say, are the major source of error, right? Quotes error, right? Error is relative. Depends on what you're trying to model and the fact that we're making a lot of simplifications, right? Error or instability in the model. If the model doesn't run at all, likely it's based on boundary conditions, right? You haven't adequately supported or you've under-supported the model, right? It has rigid body modes. It might just be able to travel in a direction in free space. And even though there's no loads applied in that direction, it might have the ability, right? We have no stiffness in that direction. Our stiffness matrix becomes singular. So when we do this, we want to make sure that we consider the fact that stiffness attracts load. Right? Over-constraining can be a problem. Over-constraining the problem can result in inaccurate load path. You might say, okay, well, this thing's just going to run if I fix all my nodes, right? Well, if you fix every node in your model, that's essentially saying that it is just frozen out there in space. There's something out there holding onto it and not allowing it to move. Right? That can have huge effects on whether or not members are adequate, what your displacements are, things like that, right? Releasing too many degrees of freedom, on the other hand, can lead to instability. Or again, inaccurate load path. Right. We have a beam element sitting on the left-hand side. It's got a point load in the center of it, right? Big difference between fixed on the ends versus simply supported, right? The ability for load to travel, right? The displacements of these two mechanisms, right? We go from here to here, right? Now we start releasing the lateral movement of that member. So we've got this versus that versus that. What does all of that do, right? It changes the ability for load to travel through our model. Sometimes we might just look at this, right? Beam element, we decide that we want to just use that, right? We're going to model in VA, we decide to put a pin at the two ends of it, of our member. Right? That member is unstable. Right? This is unstable. Why is it unstable?
Rotation of the X.
Right, yeah, x-axis. Right, this member can rotate in space. So you might have one member in a series of 1,000 that have this based on you going through and giving all the releases, right? And then the thing won't run, and the thing won't run, and you go through every single one of them, right? Talk about troubleshooting next week, but. Okay,